All right, what we've got here is obviously 2.1, but you'll see now on all of our lessons is that there's enough content in there that we split it up into multiple days. So if you're looking for kind of a reference to our class calendar, these notes would be classified as 2.1 day 1. And there'll be a few exceptions, but most every section that we cover, this is going to be the case. You know, that it's going to, if we're looking at one section out of our textbook, we're going to need at least 2 days to get through of it, because, you know, there's just a little more to it, and it's a little tougher than Chapter 1, so we slow down a bit. Chapter 2, I always like to start by just putting everything in perspective a little bit. Compared to Chapter 1, we did this like big overview of functions and saw lots of different kinds. We mostly worked with lines, but we had a couple sections where we intentionally did this big overview of function families. With a few exceptions in Chapter 2, like you're going to see today. Quadratics, that's characterized by a polynomial that's got an x squared. Cubics, x to the third. Oh, and the parent function for rational would be two polynomials that are divided by each other. That'll be a while. That'll, you know, if you're, you know, thinking of our class schedule, that'll be a couple weeks before we dive into rational. For now, the theme is going to be quadratics and cubics. We'll get above third power a little bit. We'll see 4, 5, 6 degree. We don't see those a lot, but we will. But today is all quadratics. The next lesson in day 2 of 2.1 is the same thing. Nothing but quadratics. And I mentioned this in Chapter 1, that as we continue to study functions and graphing, which is mostly what we're going to do first semester, you're going to see that theme is that each chapter in each section, we start to get more specific. And now we don't want to do this big overview of a million different functions. We want to look really closely at a couple. Okay, and that's exactly what today is about. All right, let's define it. It's a good place to start Chapter 2 because most of you're pretty familiar with quadratics. I'm going to write it in standard form. They can have at most 3 terms, a, b, and c. We do need to specify that value for a, that can't be 0. If that were to happen, the squared term would go away and we just have bx plus c. Well, that would then be a line. So that x squared term is what makes it a quadratic. So it's a big deal. It's got to be there. For the rest of this slide, let's continue to talk about a. It's a big number because it's usually the one you try to identify first if you have a quadratic expression because it tells you a lot. Probably the very first thing you're going to look for is a positive or is it negative? Okay. Now I'm going to go through this quickly because you've seen this before. If you're talking about a positive value for a, you've got a parabola or a graph that opens up. For example, if a was 1, like the good old parent function of x squared, you would get a parabola graph that's going to open up. If you've got a negative a value, which we'll see a lot, you have got a parabola that opens down. There's negative 1. Okay, those are just sketches, nothing to scale or anything like that. That's just half the story with a. There's more. Okay. Another thing that we like to see is how does it compare to 1? Now, technically speaking here, I should say absolute value because it applies to the negative cases Oh, just like the positive cases. Okay, do you have like a decimal or a fraction in front of A? That's another transformation that we saw in chapter 1, and the word that we consistently used to describe what was happening was wider. You know, how do we take a parabola graph and widen it out like that? Well, that would happen with something like 1/3, 1/4, 1/2, any decimal that's between 0 and 1. Okay, it could be negative as well. The negative is just going to mean that it's going to open down. Okay, but if you've got a number whose absolute value is between 0 and 1, that's what's going to happen. If the absolute value is greater than 1, thinner, skinnier, okay, narrower, all these terms would work. Now here's what I mean by the absolute value. Let's say we've got this nice, you know, skinnier looking parabola like 2x squared. Okay. If that were to be reflected down here, and let's say that was negative 2x squared, okay, the absolute value of negative 2 is 2. Okay, so it still has this thinner effect on the graph. Again, the negative sign, that's what we talked about first. That just means you're talking about a parabola that opens downward. Once we've established that, it's like disregard the negative. Okay, so we would really just be looking at the 2 for that negative 2, which has, you know, an absolute value over 1, so it's this case where the graph does get skinnier. All right, let's back up here. I don't want to talk about x-intercepts yet. All right. One other form that you'll see, and at the moment, both are on the page. Vertex form right up here comes up more than you would think. It's kind of tailor-made for this case if we know the vertex. Notice A is still there. And that is the same A that we just talked about. Anytime you see that in an expression, it is that number that is going to control the shape, okay, meaning narrow or wider. It'll control the shape of the graph and if it opens up or down. So that's a big number. Now, when we're talking about a vertex here, keep in mind this is if I got a parabola that opens up, it would be this point right down here. It's like the maximum or the minimum. All right. This next slide kind of focuses on how we find key points. Right? The vertex is one of those points on a graph that we really want to know because it tells us a lot about the shape in the graph that we're, you know, potentially dealing with. What I'm going to show you here is a way, and it can be a little tricky when you see it for the first time, of how you can switch forms. Okay? It doesn't always work well. A lot of times it does. But I want you to know, as I do this, my goal is to take this standard form quadratic and I want to switch it over to this vertex form. Okay, keeping in mind, as far as the number that goes out front, I already know it's going to be 2. Okay, this graph's a little bit skinnier than the parent function and it opens up. All right, here's the approach that I'm going to take. I'm going to factor out a 2 of these first 2 terms. Now I got to end my parentheses there, and then I can just put plus 7 because I didn't take a factor of 2 out of that 7. Okay, wouldn't have worked out well. It's odd. would have given me 3.5. I didn't want that. Okay, now my focus after I do that becomes right here. That's always going to be our focus, is we'll look at that number and we do something kind of weird. I'll explain it in a minute. So for the moment, you have to just go with it. And it's like, why would you want to take half of that number and square it? I just do. Okay, give it a minute, but I just do. Because here's what I do. I'm setting myself up to factor. And I want this quadratic to factor beautifully. Okay? I want it to factor beautifully. Not just to factor anyway, I want it to factor into two identical factors. Well, okay. That doesn't always work out all that well. It will if I pick the value for c, the constant at the end, if I just pick the one that I want, and I did. That was what this was all about over here. X squared plus 4x plus 2, you'd be looking for two factors of 4 that add up to 4. It's going to factor into two identical factors of x plus 2. That is what I'm looking for to happen. Okay? Now here's the problem. I can't just do what I just did. Okay? I took my expression, and it looks just like the line before, except I inserted a plus 4. Well, if that's the case, it's not equal to the line before, and I've said that it is. Okay? Now, I really, really want this plus 4 in there, okay, because it's going to factor out really nice. Here's the quick fix. I can leave it in there as long as I do that. Okay, so I want the plus 4. I got to bring in a minus 4 because 4 minus 4 is 0. So my expression is still equal to what I had before because I didn't add anything. I put in a plus 4 and I put in a minus 4. I can do that. Now my minus 4 is hanging out inside the parentheses, which I'm not okay with. I just want this part right here, because that's the part that's going to factor into x plus 2. So with these parentheses, I need to kick out the negative 4. But remember, right now it's inside the parentheses, and there is a 2 out front. Before I kick out the minus 4, I have to multiply it by 2, which means I will get this, x squared plus 4x plus 4. That's what I was looking for this whole time. And now on the outside, after it gets multiplied by 2, I now have a minus 8. And look what happens here. This factors beautifully, just like I wanted it to. Negative 8 plus 7 is minus 1. And just like that, we're done. We've switched it. And I can look at this. You always got to be careful with the number inside the parentheses. It does the opposite of what you would think. But I can now look at that and tell you the vertex is at negative 2, negative 1. Okay? We'll see more of those. And the first time you see it, it's a little bit of a tricky process, but I'll show you some more of them. That's a good one to start with. X-intercepts. Okay, let me sketch them out for you again. Let's throw on just a little set of axes here. And let's say now we've got some arbitrary polynomial that opens down. This one actually does, though this drawing is not to scale from what I have. I'm talking about these points right here. Other points, kind of like the vertex, that I want to know. Okay, you'll see x-intercepts, y-intercepts, vertex. At most, that's going to be 4 points of a quadratic graph. And we had said in chapter 1, if you're making a table of solution points, you should have 5 to 7 to make, to be confident that you could sketch those points and put together a nice graph. The more complicated the graph, typically the more points you need. okay, if I pick these points, not just any points, but the x-intercepts, the y-intercepts, we haven't even talked about the y-intercept, though it's not hard, right? It's always right there. It's -8. X-intercepts, y-intercept, vertex. I could have at most 4 points, and you could have a great look at what your quadratic graph is going to look like from only those 4 points. Okay, so they're good 4 points to choose. All right, I'm going to go ahead and factor this. If I can, I like to get rid of anything that's in front of x squared. Factoring is a lot easier if there is nothing but a 1 in front of x squared. Okay. Now, in general, I can do this because sometimes this freaks people out that I just took out the negative sign. All that does is reflect the graph. So keep in mind that this, my graph over here is not cooperating very well at the moment. It's just a reflection, so I'm still looking for these points. So taking out that negative sign, it doesn't change where those points are at. Okay? So I just leave that negative sign out there. And now I get to deal with this nice case where a is 1, and I just need 2 factors of 8 that add up to -6, x minus 4, and x minus 2, as always, and this becomes more relevant in our next example. If you want to check to see if you factored correctly, FOIL it, and if you did, you should get back to what you had before. Oh, the whole time I should have emphasized these are set equal to 0. That's why sometimes they're called zeros. X equals 4, x equals 2. Those are the 2 places this graph crosses the x-axis. Oh, let's go down and see one more. Last one for today. Oh, it's got a 2 out front. I would love to divide all the terms by 2. But that's not going to work out well with the -7, so let's not do that. Okay, if I could, I would. Instead, what we have to do is take that leading 2x squared and we just have to split it up 2x and x. Now this changes the process of factoring dramatically, because before I would just look for 2 factors that add up to -7. And the way the numbers work out on this example, that gets very tempting, right? Because what a lot of you would probably want to do, right? I'm saying plus or minus because the -30 is negative, so I have to look at one of each. I need 1 positive factor, I need 1 negative. You'd love to do that. If the difference is -7, we're good to go. But then again, when you FOIL it, you get 2x times 10, which is 20, minus 3x, which is 17x. So when we FOIL, we don't get -7 as our middle term. We got positive 17, and that's not what we're looking for. Okay, what we didn't account for by picking those 2 is the 2. When we FOILed, that 2x is changing everything. Okay? Now obviously this process is going to be dictated by how many factors you have to check. If you've got a quadratic that's got numbers that have lots and lots and lots of factors to check, this is not going to be pretty. And it's just going to take longer to look at all the cases. Now keep it in mind here as I do the FOILing process, all I have to look at is the middle term. Like the way I have this set up, okay, I know that the first term is going to come out to be 2x squared. I know the last term is going to be -30. Am I hitting this middle term of -7? So really all I need to look at are multiplying the outer 2 terms and the inner, okay? and I get 12 minus 5, which is positive 7. So how about leave the numbers there and just switch the signs, and now we get that negative 7 that we're looking for. And this is going to give us our 2x intercepts. We got to solve for them separately. This one's a breeze. One of them is at 6. Negative 5 equals 2x. Divide that by 2. The other is at negative 2.5.